online sessions are recorded, and you get a copy of that file. Okay. Apparently you have been to my website since you made the appointment online. Okay. Let's talk about logarithms, unless you have some general questions you want to ask me.
There are a lot. When we were going over this, I was sick. We did this on Monday, Tuesday, and I was sick then. So, I don't really understand how to graph them.
Well, I'll show you that, but all logarithm conversations really need to start with this. This is the exponential expression of a logarithm. For example, 8 equals 2 cubed. That's the exponential expression. The important thing to remember about logarithms is that logs are exponents. So if I want to write the equivalent expression as a logarithmic expression, the first thing I know for sure is that log equals x, because logs are exponents. So now I just have to figure out where the y and the b go. Well, the b always is the little one. It's always the base. So the only thing left is the y. So if I took that exponential expression, 8 equals 2 cubed, and wanted to express that logarithmically, it would be the log base 2 of 8, the argument, equals 3. So that is identical to that. Just like this is identical to this. And being able to go back and forth between the two is critical. You're going to, a lot of your questions you're going to get in the log section are going to be, require you to express it exponentially if it's given to you as a log expression, or logarithmically if it's given to you as an exponential expression.
Yep.
That's the fundamental of logs right there. Now you said that you weren't sure how to graph them.
Yeah.
Logs of any base pretty much all look the same. They look a lot like this. That point is 1, 0. And this function is y equal log of x. So x is your horizontal axis, y is your vertical axis. Notice that this function is extremely flat. In fact, this is probably the flattest function you'll ever see. If you went to the right on the x-axis for 2 miles, you would only go up on the y-axis 12 inches. That's how flat this thing rises. Also, notice that I didn't put a base up here. That means it's common log, so it would be log base 10. But if I were to draw y equal log base 2 of x, it wouldn't look a lot different. They all go through this exact same point, because notice that when you take the log of 1, you always get 0.
Yeah.
Just like any number raised to the 0th power is 1. So the log of any base of 1 is always going to be 0. So the log base 2 of x might look marginally different. They're both going to be asymptotic with the y-axis. But if you were looking at one alone, you wouldn't be able to distinguish one from the other. Okay? Now, we can have other stuff going on here. In other words, if you had y equal the log of x plus 1, a translation, then it wouldn't go through this point. It would go through the point 1, 1. It would still look very similar. And as long as they told you that it went through that point 1 comma 1, you could figure out that it's been vertically shifted up by 1 unit.
Mm-hmm.
And all of your transformations that apply to any function apply to logs. In other words, if you stick a 2 in front of it, it's a vertical stretch by a factor of 2. If you put parentheses around it and make it x minus 1, that's a horizontal shift to the right of 1 unit. So it follows all of your other elementary function properties. And of course, notice something significant about logs here. That is that x, the domain of this function, x has to be greater than 0. Not even 0. You cannot take the log of 0. You can only take the log of positive numbers. And furthermore, when you take the logs of numbers greater than 1, you get positive numbers. When you take the logs of numbers between 0 and 1, you get negative numbers. So the range of the function is negative infinity to positive infinity. But the domain is x strictly greater than 0.
Right.
It's different than the square root function. It looks a lot like the square root function. If I wanted to plot the square root function, you might have a difficult time telling them apart, except for the fact that the square root function begins at 0. It doesn't have any values less than y, because y is always positive for the square root function. But notice that it's not asymptotic with the y-axis, like the log function is. Now, I should say before I go much further here that typically I don't do all the talking in a session. I really attempt to engage the student. So it's usually going to be me saying, what kind of problems do you want to do today? You verbalizing them, me writing them out, and then me asking you, okay, what's the first step in solving this? And so I'm constantly trying to get you to solve the problem, not just acting like a teacher, lecturing, telling you how to do it.
Good.
Okay? So that's one of the things. If we're going to do sessions, I would like you to bring material or problems to the session. And you can either, usually with online sessions, the student either verbalizes them, which you can do with most math, or if they're like graphical in nature, just take a picture with your smartphone of the review material and send it to my email address. And then I bring it up on my screen, and it's like we're sitting next to one another looking at the review material.
All right.
Do you have any problems that you'd like to present right now that we can look at?
Specific? It will
Yeah,
say me that
yeah,
you're specific problems.
specific problems from your chapter or homework.
I don't really know how to add logarithms. Like, that's one thing I don't really know how to do.
Let's talk about that. The 3 most important equations regarding logarithms. One is this one. If you have the log of 2 things that are being multiplied together, then that's equal to the log of 1 plus the log of the other. If you have the log of 2 things that are being divided, that equates to subtraction. That's the same as the log of A minus the log of B. And the third one is if you have exponentiation going on. In other words, if you're taking the log of A raised to the B power, then we multiply it. B times the log of A. So all of your class problems that say expand or contract, these are the 3 formulas they're talking about. An example, if I said, what is the log of 3x? Well, that's the log of 3 plus the log of x. As long as you have the same base. I guess to be technical here, I should put of a particular base, and all of these bases have to be the same. Not this b here, but in other words, I wouldn't be able to say that the log base 7 of AB is equal to the log base 5 of A plus the log base 5 of B. You have to maintain the same base in order to do these three rules.
Yeah.
So let me quiz you on that. Let me make up some problems here. If I said, what is this equal to? Expand that. Based on Rule 1 and Rule 3.
I don't really know.
Okay, let's do it one step at a time. We have multiplication going on. We have x squared times y. So it's going to be the log of x squared plus the log of y. Because we have multiplication, we're going to turn it into addition. Thirdly, we have one of these terms is the log of x squared. Well, by rule number 3, I can take this 2 and stick it in front. So that's what that thing expands to, is 2 log of x plus the log of y.
Okay.
Okay? Pretty straightforward once you do a few of them. Let me do another one here. Again, let's do it in 2 steps. Let's separate the multiplication going on. And then we got division going on, and we know division is subtraction. So I'm going to end up with what?
It will be log to the x of 3 plus b log of y to the 2 minus the log of e to the 4.
And now, to fully expand it, bring all those exponents down.
So it would be 3 log x plus 2 log y minus 4 log b.
Perfect. Okay. These can get harder.
All right.
In general, Chatfield has a pretty difficult curriculum.
It just all depends on what classes you take.
I'm sorry, what?
It just depends on what classes you take.
Oh, yeah. Okay, yeah, I suppose. I tutored quite a few calculus students from Chatfield, and it seems like their calculus curriculum is tougher than just about any other in the state that I work with.
There's only a AP Calc at Chatfield, so yeah.
That's probably why.
Yeah, there's no normal calculus.
No, there isn't. Okay, that explains it.
All right.
So we got division going on here. So what's the first step to separate it, to expand it? Subtraction, right?
Yeah.
Like that. And now, instead of the radical sign, let's use exponential notation. That's the same thing, right?
Yeah.
I mean, square root of y is the same as y to the 1/2. Once we have it in exponential notation, we can bring the exponent. So now we have log x minus 1/2 log y. So
All right.
that's expansion. Now let's look at condensing. We don't have too much time left. And unfortunately, I don't have a lot of leeway today. I have another appointment I'm going to need to leave right at 4:30. Let me think of one here that we can condense. What if we had this? And let's go ahead and make an equation out of it. Let me think for a second. Now let's start with that. Have you gotten into solving log equations yet?
Kind of, and I have no clue how to do that.
Okay. Well, the way you do it is by using those rules. In other words, if I didn't make this an equation, let's just condense that. What does that condense to? In other words, you've got two logs being added, which means I can condense it to the log of two arguments being multiplied together. See that step?
Mm-hmm.
Okay. If I do multiply those together, I get this. So, let me think for a moment here. So let's see, if I wanted to turn this into an equation, let me do that. Which now means I can say the log of x squared minus 1 equals 1.
Mm-hmm.
Now where do I go from here? How do I solve that? The answer is to turn it back into an exponential expression. Okay? Here's how you go backwards. In other words, remember logs are exponents. So the exponential expression here is whatever the base of that log is, which is 10, raised to the number on the far right, which is 1, has to equal the argument. 10 to the 1 is 10. Now I have a quadratic that I can solve. In other words, if I solve this, I get x squared equals 11, x equals plus or minus the square root of 11. There's my answer, but be careful with logarithms. Almost always, one of the answers is extraneous. It doesn't work.
Yeah.
Notice that if I plug in the minus square root of 11 into the original function, I end up taking the log of a negative number.
Yep.
So the only answer that I really have is the plus square root of 11. And that works because square root 11 is 3 and change, so it doesn't violate the domain. But you have to be very careful about violating the domain on logarithms. More importantly, what's really strange is that you have to go back to the original expression, not this expression here where it's put together. In other words, for all practical purposes, this is an equation that I've written right here that I'm pointing to. But for domain purposes, it is not. In other words, if I were to say, okay, this leads to this, and I have that's equal to 1, and now if I go back and I stick in plus or minus root 11, I don't violate the domain at all because I square it, and it becomes positive regardless. However, we are violating the domain with that because we have to plug it into this equation here. And the moment you plug it in the minus root 11, you violate both that and that.
Yeah.
So only the plus root 11. So in reality, these aren't exactly the same. They don't have the same domain considerations. You always have to go with the initial domain considerations. Might seem like a subtle point, but if I know Chatfield right, you'll have 1 or 2 questions on that where you have to be careful about checking your domain.
Yeah.
Okay. Garrett, why don't we stop there? Hopefully I've helped you a little bit out on your logs.
Yeah. Thank you.
You should have a little bit of an idea on my tutoring style, although I swear I don't talk as much as I did this session, usually.
Yep.
So you know how to schedule on my site. So if you want to set up another session, you're in position to do so. If you don't see an opening that you're looking for, or it's you need to give it 2 hours notice if you're going to schedule on the site. But say you only have 1 hour's notice, feel free to call me or email me or text me or whatever you like. And if I have a time open, I'll certainly accommodate you.
All right.
Okay.
Sounds good, David. This is John here.
Yeah.
So I'm happy to write you checks. We don't have a PayPal account.
That's fine. I have no problem with you sending a check. I'll just.
It's on your brochure where I would send a check to.
I think it's on the brochure. I'll write my address. There's no charge for this session, but for future sessions, if you don't want to know where I live, here's my address. Is that on my brochure?
You know, I just don't have it in front of me.
I don't think it is. I don't think it is, but that's my address.
Okay, and so we're familiar with the procedure for setting up appointments. How about when it's time when the time has come around to actually have the session? Do we just launch?
What I usually do is text the meeting ID number to the student, to their cell phone. I don't call, because the only thing you need is a meeting ID number. Yeah, you just need to launch the GoToMeeting or the Join GoToMeeting program. And with a meeting ID number, you're hooked right into the meeting. Okay,
sounds good. But you said you text that. What number did we give you?
Let me look. The one I first called, is there a different one I should use? I've got the 948.
You can't receive text messages on that one.
Okay. I tell you what, can you put Garrett's number when you sign up for a session? Use his number, and then I will just text it to whatever number is in the sign-up.
Okay. Okay, and you're talking about the appointment setting part?
Yeah. In other words, when you make the appointment, they ask for a phone number. Just go ahead and put the one that I can text a message to.
Okay, great.
All right.
Sounds good. Sounds relieving. Thanks, David.
It is.
All right, thank you.
All right. Nice meeting you, Garrett. Talk to you later. Bye-bye.
See you.